Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all in class of elementary number theory by David M. Burton. My name is Azmat Ali and I welcome you all at my channel Academy of Mathematical Sciences. Our discussion is continue on properties of GCD. So related to the properties, in today's lecture I will discuss question number 4 A and B parts from problem 2.4. Question number 4 says, if A and B has a GCD equal to 1, then we have to show that GCD of A plus B and A minus B is equal to 1 or 2. Its B part says GCD of 2A plus B and A plus 2B is equal to 1 or 3. I will share two different techniques to solve both of these questions. So let us discuss the first part. We suppose that the GCD of A plus B and A minus B is equal to some positive integer D. Suppose GCD of A plus B and A minus B is equal to some positive integer D. If D is the GCD of these two numbers, then according to definition, D must divide both of the numbers. This implies D divides A plus B and D also divides A minus B. Now by using the definition of divisibility, there must exist two integers k1 and k2 says such that there exists integer k1, k2 belong to Z such that this number A plus B, that is dividend, this can be written as A plus B is equal to K1 into divisor D. Say this is my equation number 1. Similarly, there exists an integer K2 for this division. We have A minus B is equal to K2 times D. I hope you are familiar the definition of divisibility and the definition of GCD. Otherwise, you can watch my previous lectures in which I have briefly discussed the concept of divisibility and GCD. Say this is my question number 2. Now from these two questions, I want to eliminate the value of A and B. Firstly, if I add 1 and 2, I can obtain I can obtain the value of A. So by adding 1 and 2, we have 2A is equal to K1 into D plus K2 into D. Taking D common from here, we have D times K1 plus K2. This is equal to 2A. Now if I subtract question number 2 from question number 1, we can obtain the value of B. Subtracting 2 from 1, we have 2B is equal to K1D minus K2D. Taking D as a common from here, this becomes D times K1 minus K2 2 times B. Now I am going to find the GCD of these two numbers 2A and 2B. Okay. Next, the GCD of 2A and 2B, this is equal to GCD of, what is the value of 2A? 2A is equal to D times K1 plus K2, comma, value of 2B is equal to D times K1 minus K2. For the left side, I will use a property that I have discussed in my previous lecture, which is actually theorem 2.7, available in this book. That property says that GCD of KA KB is equal to K time GCD of A comma B, where K is positive integer. That is, we can take K as a common from both of the numbers. So applying this property, our K is 2 here. So we can write it as 2 times GCD of A comma B is equal to, same property we can use for the left side here, right side, sorry. This becomes D time GCD of K1 plus K2 comma K1 minus K2. As it is given that GCD of A and B is equal to 1, so this becomes 2 into 1, that is 2 over GCD of K1 plus K2 comma K1 minus K2 is equal to D. Say this is my star. Now I have to prove that our GCD, our D is just equal to 1 or 2. If you focus on the left side of star, if you focus on the right side of star, this is D. D is an integer which should be equal to 1 or 2. This is not a fraction, not any real number. This is just an integer which have values 1 or 2. Now this is possible that if the denominator exactly divide 2, now the divisor of 2 are only 1 and 2, positive divisor of 2 are 1 and 2. So from star D is a positive integer, as D is positive integer, which should be 1 or 2. This is possible if the denominator, that is GCD of K1 plus K2 comma K1 minus K2 is equal to 1 or 2. So when your denominator is 1, then it becomes 2 over 1. In this case, our GCD is 2. In case when your denominator is 2, then our D is equal to 1, which is required to prove. Next, I will discuss its second part. You can solve the second part by using the same style, same technique, but I will give you another style to solve the second part, and that style you can use for this part also. Okay, next we discuss its B part. To prove this part, I will use the concept of linear combination. In my previous lecture, I discussed that GCD is the smallest positive integer that divides every linear combination of the corresponding integer. Linear combination means sum of product form. So firstly, we suppose the GCD of these two numbers is D. Suppose GCD of 2a plus b and a plus 2b is equal to D. Then D must divides every linear combination of these two numbers. Linear combination of means if a and b are any two integers, then their linear combination is of the form ax plus by. This form is called linear combination form. Linear combination of A and B. This form is called linear combination of A and B. So its linear combination mean this is the form of 2A plus B into X plus A plus 2B into Y. D must divide this linear combination. Now I want to use the technique that I have to substitute such value of X and Y that this sum becomes equal to 2A and 2B. So which values of X and Y will work here? It is very easy. If I ask, I want to eliminate B from here, what will you do? We will multiply equation number. Suppose this is my first equation. Suppose 2A plus B. This is my first number. The second is A plus 2B. I will multiply this number by 2 and this number with minus 1. And then after subtracting, this becomes 2 times 2A plus B, and multiply this number by minus 1. A plus 2B. Now if you solve this number, this expression, this becomes 4A plus 2B minus A minus 2B. 2B is cancelled, remaining is 3A. So remaining expression is equal to only value of A. So if you compare here value of X is equal to 2 and value of Y is equal to minus 1. So this is very simple. You have just to think that for what value, for what coefficient you can multiply with this number and then subtract the resulting expression with this number, and your result should be equal to just value of A. So we will write D, if D is the GCD of this number, D must divides every linear combination of of 2A plus B and A plus 2B. So we can write here D divides, because D divides every linear combination. So we can say D divide in particularly 2 times 2A plus B plus minus 1 time A plus 2B, and this linear combination is, after simplification, this is equal to 3A, sorry. This shows A divided 3A. Similarly, now I want to eliminate the value of A from here. So if we multiply the second number by 2 and the first with minus 1, and after adding A would be cancelled. That is, if we multiply the first number with minus 1, this becomes minus 2A minus B, and the second number with 2, this becomes 2A plus 4B. This gives equal to 3B. Again we will write similarly D divide the linear combination minus 1 time first number, that is 2A plus B plus 2 times second number, that is A plus 2B. Okay, this is equal to D divides 3B. Now here D divides 3A and here D divides 3B. It means D is the common divisor of both numbers 3A and 3B. As D is the GCD, GCD is the smallest positive integer that can be expressed as a linear combination. This is base of lemma. That can be expressed as a linear combination of A and B. This implies D must divides GCD of 3A and 3B. Sorry. As D is the common divisor of 3a and 3b, it means D must divides the GCD of 3a and 3b. GCD means greatest common divisor. D is the just common divisor. It means D must divide the greatest common divisor. By using theorem 2.7 that I have discussed in first part, we can take 3 as a common because 3 is a positive integer. This can be written as 3 into GCD of A and B. As GCD of A and B is equal to 1, so this becomes D divides 3 because GCD of AB is equal to 1, this becomes D divides 3. As D is the positive integers and it divides 3, there are the only two positive divisor of 3. There are the only two possibilities for D. This implies D is equal to either it is equal to 1 or it is equal to 3. That is required proof. So inshallah in the next lecture we will discuss its remaining two parts, C and D. If you find this lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.